This is a summary of Gibbs free energy and the equations we need to use to find Gibbs free energy and what it tells us about a reaction. So first of all, delta G naught, so that's referring to the standard Gibbs free energy change for a particular reaction. We can use a modification of Hess's law, which involves, instead of the heats of formation for the substances involved in the reaction, we can use the Gibbs free energies of formation. So same idea, it's if we formed a substance from its elemental states, the Gibbs free energy change for that process, that's the Gibbs free energy of formation. So these values would, much like the delta HFs, also be 0 for elements in their regular elemental state at 298 Kelvin. Notice we're doing the sum of the products minus the sum of the reactants. They're delta GFs, and we are multiplying by the coefficients. That's what the N and the M's stand for. So that is that same equation we've used for both enthalpy and entropy now. So that's one way to find Gibbs free energy change for a reaction. And if you are given Gibbs free energies of formation, then that's the equation you should use. Remember that the naught, I already mentioned, means 298 Kelvin, but it also then specifically refers to, if I'm talking about a reaction, the Gibbs free energy for a reaction, that is specifically for if there's a gas species that it's at 1 atmosphere of partial pressure and that solutions are at 1 molar concentration. We would also then be assuming that the liquids and solids are pure liquids and solids. So another variation of this equation that we've also talked about is that delta G can be related to the enthalpy and entropy, because we said the effects of the energy changes and the entropy changes, those can drive a reaction to occur spontaneously without outside intervention. And so this equation incorporates those two thermodynamic variables to help us then assess delta G. And so we've got the change in enthalpy for the reaction minus T times the change in entropy for the reaction, and that will give us the delta G for the reaction. So if we're given delta H data, delta S data, or enthalpies of formation and entropies of substances, we can find those values to plug into this equation and find delta G in this manner. And one thing that we have to be careful of is dealing with non-standard conditions. So if we're given a problem where we have the information with which to find delta H naught, delta S naught, but then we're asked about the reaction happening at some other temperature, although delta H and delta S are not exactly what they would be at the standard conditions, they wouldn't be exactly the same as they would be at the the new conditions that the problem is referring to, but we can still at least use them for a pretty close approximation. So if you're asked about solving for what if we increase the temperature to 1000 Kelvin, or what if we run the reaction at a low temperature at 100 Kelvin or something like that, you can still plug in the temperature that's mentioned in the problem and the enthalpy and entropy naught values, and still use that to get a decent estimation of your delta G. And so now we're going to switch over to worksheet C. So I recommend that you pull this up or print it out or have it somewhere available, and we will take a look at the first problem. We're actually going to look at problem 4 on worksheet C. And so problem 4 is giving us some information about this reaction. It says calculate delta H for the reaction, and using thermodynamics data from Appendix C, and then the couple of things that are not available in Appendix C are given to us right here. So that's going to be using that Hess's law equation, products minus reactants times coefficients. Predict the sign for delta S. So think about that for a minute, and then you can pause the video, try the calculation for A. For B, try the prediction for delta S. C, we're going to do the calculation. So again, using that Hess's law variation involving entropy values. And then lastly, for D, we're going to use that delta G equation that involves both the delta S and delta H that I just gave you. And then we'll look at the spontaneity. So pause the video, try the problem, and then restart me when you're ready. All right, so I'm going to assume that you kept yourself honest and actually did the calculation yourself. So these are what the delta H numbers would look like. It comes out to negative 1,316.8 kilojoules. We're going to predict the sign for delta S, and if you look at the fact that we have 2 moles of gas plus 2 moles of gas plus 3 moles of gas, and then we're forming 2 liquids, we're going to predict a very negative delta S because we're going from all gases to all liquids. That's got to be a decrease in disorder. So when we actually execute the calculation, there are all the numbers there from the appendix, and you end up with a negative 658.3. Notice that the units for entropy are joules per Kelvin. And so when we go to use the delta H and the delta S, we need to be careful about matching units. So I've recommended before that you convert the joules to kilojoules, because otherwise we're going to end up with astronomically large values. Usually kilojoules is an appropriate unit for delta G. So we're going to plug into the delta H minus T delta S, and so those, you see those numbers here, we're taking the delta H there, minus, we are told that we're working at 298 Kelvin. There is this number in kilojoules per Kelvin, and there's the value that we get. So the fact that this comes out to be a negative delta G, we said that we would predict this reaction to be spontaneous at these conditions. And again, if we think about this reaction is very exothermic, so negative delta H is, in the thousands. And so even though the disorder is decreasing, which is not favorable, our temperature is low enough that we still end up that this release of energy is enough to compensate and drive the reaction. So we end up with a negative delta G, and so this reaction would be spontaneous. All right, so we're going to switch back to our notes. And all right, so here we're looking at the delta G for, or how the delta G will come out if we have a different delta H and delta S scenario. And there are some times where the reaction is always going to be spontaneous regardless of temperature. And so under those conditions, we have the very favorable negative delta H and the very favorable positive delta S. And so that is a winning combination, cannot have anything but spontaneous. So no matter what temperature we work with, we're going to end up with a negative delta G. Likewise, we can also have a very unfavorable system where we have a positive delta H and a negative delta S, both of which are not favorable at all. And so certainly there is no temperature scenario that will make that work. And again, when I say a reaction will not be spontaneous, that doesn't mean that we couldn't force it to happen through outside intervention, but it's not going to happen of its own accord. So then we have these other two scenarios where, let's say we have an exothermic reaction, so we end up with lower energy for the system, which is good, could be a driver, but if delta S is also negative, then there's this temperature factor that has to be considered. So if we were to have a negative delta H and a negative delta S, this reaction will be spontaneous at low temperatures, and that's because this negative T delta S term will be positive. And so if we're at low temperatures, then this T delta S that's positive will not outweigh the negative delta H value, and therefore the reaction will be able to be spontaneous, and we'll see that negative delta G. We see the reverse or opposite happening here, the unfavorable positive delta H, the very favorable positive delta S. So which one's going to drive the reaction? Well, again, at high temperatures, we're going to see this, the T delta S term is going to be a negative value, and at high temperatures that will be a very large value. And so as long as that negative comes out to be larger than the positive delta H, we end up with a spontaneous process. Okay, so the other thing to keep in mind is that there's this relationship. We're eventually going to get into looking at equilibrium, and we know that most reactions can be thought of as reversible, and many reactions are truly reversible, where they'll, reverse to some degree and then reach equilibrium, assuming they're in a closed system. So if the delta G for the forward reaction is negative, then that would mean that the delta G for the reverse reaction would have to be positive. So keeping that in mind, we'll eventually get to addressing equilibrium and what to do about that. So the magnitude of delta G will decrease as a reaction proceeds. So that means it's getting less negative, because that delta G value is in reference to the amount of available, the energy available to do work. So, the value will approach zero and become zero once the system hits equilibrium. But again, the important thing is that delta G will decrease and become less negative as the reaction proceeds. And so again, when we finally have that balance between the forward and reverse reactions get going, we will get to a point where delta G will be 0. So that's also another important thing that will then drive our future equations that we come up with. And when we are looking for the conditions under which, or the temperature at which a reaction actually becomes spontaneous. So when we look at these last two scenarios on the table up here, when I have an exothermic reaction that has a decrease in entropy, and I want to know, well, what temperature is this going to happen at? Like, how low is low enough for it to be spontaneous, or how high is high enough for the temperature for this fourth scenario to be spontaneous? Well, now we're going to look for that to calculation 5 on worksheet C. So let's take a look at that. And this is, says, show the reaction not spontaneous under standard conditions by finding delta G. Okay, so if you're just given something like this on a test, obviously you'd have to be given some data with which to do this. For this one, I would say go look in your Appendix C for the delta GF values. That would be the simplest way to accomplish calculation 5A. If it's not spontaneous, so if we're showing that, what we'd be looking to demonstrate is that there's a positive delta G. So remembering that that's our target, what we're looking for in a question like this. So for B, find the temperature at which the reaction becomes spontaneous at standard pressure. Let's think about that. So I'm going to go back to this equation right here. And so the temperature where it becomes spontaneous, if you think about this equation here, a lot of times you'll see the delta G being set to 0, and then you'll kind of solve for rearrange things and solve for temperature. But if we think about why we would do that, again, if this value is negative, it's spontaneous. We want to kind of catch that point where we transition from negative, or from positive to negative. So our objective here is to figure out, basically whatever delta H is. If delta H is 5, then, if we have negative T times delta S, well, we'd want this to be greater than 5, right? So just as an example, if this is 5, we'd want to be subtracting off a number that's greater than 5, because then that would end up with a negative delta G, which would indicate the reaction spontaneous. So that's kind of where the logic lies with when you're told to set this delta G equal to 0. We're basically trying to find that balance point where this term becomes negative enough to overcome the delta H. So that's the method that we're going to employ here. So when we look back at the worksheet, that's what you're going to try. So essentially you're setting delta G equal to 0, rearrange and solve that equation for T, and then you can pause the video while you're doing that, and then come back and we'll talk about the answer. All right, so hopefully you have actually done your calculation. Notice that looking up the values from the back of the book, positive, non-spontaneous, 5.40 kilojoules. It's not that large of a value. So when we look at then what I just said to do for figuring out what temperature the reaction becomes spontaneous, well, I guess I should have mentioned where do you get delta H and delta S from? We saw that in the previous problem. If I have to find delta H and delta S, go calculate them with the reference information in the back of the book. On a test, of course, you would be given that, or some other problems you might be given a table. Anyway, I find delta H, you get 58.02 kilojoules. I find delta S, you get 176.6 joules per Kelvin. Of course, that needs to be converted to like units when we're working with an equation that involves delta S and delta H. So I do that. So notice I'm plugging those values into this equation and rearranging and solving for T. Essentially, this equation is always going to come down to, if you think about, where is that equation? Is it up here? Of course not. If you think about that delta G equals delta H minus T delta S equation, when you rearrange that and solve, it's always going to end up being delta H divided by delta S gives you the temperature. But again, we don't want to have extra equations memorized. We can very easily solve for that if we understand why we're doing what we're doing. So anyway, we solve for 329 Kelvin or above is going to be spontaneous. And again, if I plug that number back in, I can see that 329 times 0.177, that would be the break point, the switch point where, you know, this negative value would be equal to the positive value. So any temperatures higher than that would get me an overall negative delta G value, and that would mean that we're spontaneous. All right, moving along to our next slide. Oh, there's of course our equation, and it's not coming up. Anybody? Okay. All right, so I guess it all came in all at once, right in one shot. Okay, so let's look at what this says here. So every once in a while, we have, well, actually more than every once in a while, we're not at standard conditions, so we're not able to use naught. And so when we find that delta G naught, we have to be able to adjust for, well, you know, what if I'm at not 1 atmosphere pressure? Because honestly, most of the time, we're not going to have 1 atmosphere of a partial pressure for a gas. We're going to have something else. Same thing with our solution concentrations. Many times we work with concentrations other than 1 molar. So we should be able to adjust for that. So that's what this equation here does. And notice that we see the delta G naught. So you'll still need to find this. You'll either be given it or you can find it from the methods we've already talked about. So like the delta G formations using Hess's law, plug into that. That plus this adjustment factor. So we've got R T times the natural log of Q. So these players we've seen before. Of course, temperature is the absolute temperature in Kelvin. R is the universal gas constant, but it's got the unit of joules per Kelvin times mole. So we haven't really utilized this version of R back when we were doing the gas laws, but it does come in handy, this numeric version with these units. And notice that it's in terms of joules, our energy unit, which makes sense to use in these problems. And then Kelvin times, per Kelvin times mole. So that's a constant that gets plugged in. Again, this is sort of an adjustment factor for not being at 1 atmosphere and not being at 1 molar. So that's where these units kind of, you know, if you went in and derived all the units, why this works. It has to do with those conversion factors between them. So then we look at natural log of Q. And so remembering that Q is the symbol for the reaction quotient for a system that's not in equilibrium. And how we find that is what it says in red here, which is to plug the current pressures. And if we're working with pressures into the equilibrium expression, they need to be in atmospheres. If we're working with a Kc, or like an equilibrium expression in terms of concentrations, we would need to plug in molarity. And then we're plugging into the expression and finding Q. So remember that Q is, if I plug into the equilibrium expression and I'm not at equilibrium, that's the definition of what a reaction quotient is. So again, we're not equilibrium conditions, we're not standard conditions because we're not that 298 Kelvin, we're not the 1 atmosphere, and we're not the 1 molar. So we're plugging in, finding Q, and then this factor adjusts the standard Gibbs free energy to the conditions at hand. So that's one problem that we'll take a look at. The second thing, though, is if we remember what we've talked about so far. We said if a system's at equilibrium, that, well, Q is equal to K. So we're going to make some substitutions into this equation. So if we're at equilibrium, Q equals K, right, because the concentrations would give us that equilibrium ratio. The other thing that we just got done talking about is that at equilibrium, delta G would be 0. Now, we're not talking about delta G naught. We're talking about delta G, right? So this one that we're solving for at equilibrium would be 0. So if we rearrange things, right, so we'd be putting a 0 in over here for the delta G, we'd be putting in a Q in place, or sorry, K in place of the Q, rearrange and solve. What you end up with is this. So you get delta G naught equals negative RT natural log of K. This is sometimes referred to as the Ratlink equation. And the reason it's called Ratlink is because it kind of sounds like a word. It's a nonsensical word, but nonetheless, it pretty much tells us the components that we would need to use. And this equation is also going to be one that appears on your AP equation sheet. The most common use of this equation is if I have an equilibrium constant and I need to find a delta G and I don't have all the other types of information that we've previously talked about, you can use this to find a Gibbs free energy, tell if the reaction is spontaneous or not in the particular direction. The other thing is that if we rearrange this equation, we now have a new way to solve for the equilibrium constant. So have you ever thought about, the lab we did with the iron thiocyanate, and, we had to measure the concentrations, and we had our method for measuring the concentrations of the, because it was a colored species, we could use the colorimeter. Well, what happens if I've got non-colored species? How am I supposed to ever measure an equilibrium constant or get those concentrations? So this gives us yet another tool for finding an equilibrium constant, and it is by looking at the Gibbs free energy of the reaction. So K equals e to the negative delta G naught divided by RT. One thing to be very, very careful about, delta G's are usually in kilojoules. The R value, this one is given to you in joules. There's another worksheet that it's given to you in kilojoules, so this would be 8.314 times 10 to the negative third kilojoules per Kelvin times mole. So be very, very careful with those units. So other than that, though, it's just plug it into the equation. You don't have to have this one memorized either, because if you know how to get, we'd plug in the delta G, the R, the T, we can solve for natural log of K, and then we know to get something out of a natural log, you would that would be base E. So it would be E to that value would give us the K. All right, so we're going to switch over to our worksheet again. And now we're going to look at problem 8. So we want to get that out. And so there's all the background information we just talked about. And so for 8, it says calculate the delta G at 298 Kelvin. So we have that standard temperature. However, the pressures that we're given, not 1 atmosphere. Like this one happens to be 1 atmosphere, but if they're not all, then we're not at standard conditions completely. So how do I find delta G? Well, I'm going to use that equation we just talked about, this one right here. And we need to find delta G naught first. So that's the thing that doesn't explicitly say in the problem. So you're going to have to go to the thermodynamic table in the book and delta GFs all the way through for this reaction. And then we're going to figure out the Q. So remember that the equilibrium expression is, in this case, we're dealing with pressures, so we should put P instead of the bracket notation, but it's going to be the pressure of NH3 squared, because it has a coefficient of 2, divided by the pressure of nitrogen times the pressure of hydrogen raised to the 3rd power. So you're going to find Q, find your delta G of formation, using the delta G's of formations, plug in and check back, and let's see what we get. You better pause and try it. I can see you. Make sure you pause it. Okay, so we're back, and you have done the calculation. I know it. You can feel it. You're not just jumping ahead. Okay, so it's kind of a pain to look up all that stuff. I get that. So here's the Q equation that I just mentioned. So I'm plugging in these concentrations, so making sure you put everything in the right place. So there is the 0.5 squared, there's the 1, and there's the 3 cubed, and so we get a, oh, it's cut off on the paper. You had to use your own calculator, or else you're not going to be able to see the number. Oh my goodness, it's terrible. Okay, so, well, oh, there it is right there. So natural log 9.3 times 10 to the negative 3rd. Notice that I'm doing my unit conversion right here for the R value. There's the temperature, because we're told we're at 298 Kelvin for this process, and this is the delta G of formation, or delta G from the delta G's of formation. There they are from the back of the book. Remember that the elements, delta G of formation is 0, so you really only had one number to look up. That wasn't so bad. So you plug those in, get negative 33.32. Plug that into the equation, and we get a delta G of negative 44.91 kilojoules. So there's our answer for that one. And then we move down to calculate the Kp for the reaction in problem 8. So again, you better pause it. But let's think about this. So at equilibrium, we said that we would have this scenario here, right? So the delta G is 0. Delta G naught is still the delta G naught, so it's still the negative 33.32 that we just figured out, so we get to reuse that again. That's good. The R and the T are still the same, but this time, again, the natural log of K is going to be that's the thing we're missing, that's the thing we're solving for. So we no longer have, these non-equilibrium conditions, right? The numbers we were initially given in the problem. So we're looking for, well, what is that ratio going to be of this expression at equilibrium? And so we plug in plug everything in, and then solve it up, and you end up with 7 times 10 to the 5th. So what that tells me about this reaction, again, don't forget what all this means. That means that my forward reaction equilibrium position at these conditions, equilibrium position lies to the right, Very large, greater than 1. Equilibrium constant tells me that the reaction equilibrium lies to the right. And so that's important to remember. And there is a sample calculation of finding K. You might also be given problems where you have a K and you need to solve for other stuff. You can use it to find delta G then. So just make sure that you remember, whatever you're given, look for which piece of information you have, which equation has those pieces of information in it, and then try to find a way to work it into the piece of information.